tension and compression with either they are equal or no. So as you can see, for our material, the tension and the yield strength of the material at tension and compression is equal. So in this case, we have to follow this line, because here is asking whether the yielding stress in tension and compression is equal. Yes, they are equal. For in our example, they are equal. So we have to follow this line. Okay, when we go through this line, there's another question whether your design is conservative or no. So depends on the conservativity of the design. If it is conservative, we will follow and use maximum shear stress theory, and if it is not conservative, we can use the distortion energy theory. The meaning of the conservative here, I will explain later in the example. Okay, in the part A, we have this state of stress. The axial stress in x direction 70 kpsi, in y direction 70 again 70 kpsi, and in the shear stress equals to 0. Okay? Okay, so what we are going to do, we will find the factor of safety for each one of these state of stress by using these two theory. That means the maximum shear stress theory, we normally we write by MSS, and distortion energy theory we shows by DE. Okay, so we are going to find the factor of safety for each one of these state of stresses. Okay, in part A, the stress of stresses is sigma A and sigma B equal to 70. Okay, to find the safety factor by using the distortion energy theory, we can refer to equation at this chapter. Let me show you the equation. Okay, in general state of stress, uh, when we have three principal stress, because we are talking about the 3D elements, right? When we have three principal stress, we show principal stress by sigma 1, 2, and 3. You can find the effective stress or one misses stress by using this equation, equation 512. One misses stress or effective stress. If we have only two principal stress, when we are talking about a two-dimensional element stress, that means the sigma 3 is 0. When sigma 3 is 0, then we have only sigma 1 and sigma 2. We use sigma A and sigma B to show them. Okay, so that means sigma A and sigma B is the only two principal stress, and sigma 3 is 0. Okay, so in this way, the effective principal stress can be found by equation 513. You know that to find the principal stress, you should use Moore-Circle theory, right? If you don't like to use Moore-Circle theory, you can directly use one of these two equations. That means you can substitute the state of stress in terms of x, y, z components directly into this equation. So if you have x and y, z components, you can directly substitute into this equation to find the effective stress without needed of using Moore-Circle theory to find sigma A 2, sigma 1, 2, 3 first. You can directly use this equation. Also, again, if you have only two, stress in terms of x and y, z component, you can use this equation directly to find effective stress. So it's up to you. You can either first find the principal stress or directly use this equation. So let's refer to our problem. Here, the principal stress sigma A and sigma B is already given. So we don't need to use Morse-Seeker stress, and we can use this equation because principal stress are given. Then I will substitute to this equation, as you can see, right? Sigma A times sigma B, and sigma B square, right? And I will find the effective stress. To find the safety factor, we have to divide Sy by sigma prime. Sigma prime is the symbol for showing the effective stress. We show effective stress by using sigma prime. So the safety factor is 1.43. Okay, now I want to use maximum shear stress theory the to find the safety factor. Okay, first of all, let me explain something. When we have a sample in the lab, if we have a sample similar like this, usually maybe you have seen that in your strength of material subject, a sample something like this. Normally we use this such sample to use train to make a stress test, right? Then we apply the load in these two directions. We pull this sample. So in this case, if we, for example, we call this x direction, we are pulling the sample in one direction. So if I draw the Morse circle for this sample, there is only one circle. Let's say this is sigma 1, which is equal to sigma x, and here is, for example, sigma 2, which is 0, right? So in this case, as you know, this is the shear stress and this is the principal stress, right? Or axial stress. As you can see here, the maximum shear stress tau max equals to radius of the circle, right? Tau max equals to radius of this Morse circle, and the diameter equals to sigma x, right? So this radius is sigma half of the diameter, right? So sigma x, right, divided by 2. This sigma x at the yielding point is Sy, right? If we pull this sample until reach to the yielding point, that means, for example, I draw this strain, stress diagram. The yielding point here, somewhere here, as you know, we should draw a parallel line to the elastic region at 0.02, right? Somewhere here is the yielding point equals to Sy. Okay, Sy, yielding point. So maximum shear stress at the yielding point is Sy divided by 2. Okay, maximum shear stress at yielding point, let me write here, at yielding point equals to Sy divided by 2, or yield strength divided by 2. Okay, so Okay. In next action, I have to find the maximum shear stress for this state of stress. Okay, as you can see here, we have two positive principal stress. So let me explain different case that uh, we will face when in different state of stress. Okay. Normally we have three case. In case one, we have two positive principal stress. Two positive principal stress. Normally, if we have three principal stress, we use sigma 1, sigma 2, and sigma 3 to show them. If we have only two principal stress, we use sigma A and sigma B. Okay, so when we have three principal stress, we use this way, and when we have two, we show. So that means when we have sigma A and sigma B, that means another principal stress is 0. Okay, so in case 1, we have two positive principal stress. Okay, let me draw the more circle, okay, of these two principal stress. This is sigma A and this is sigma B. Okay, what about the third? Yeah, there we don't have the third principal stress, but actually the third one is 0. So that means we have another principal stress which is 0. And then I have to draw another circle here. Another circle for these two principal stress and another circle for these two principal stress, sigma A and the third one which is 0. Okay, although the third principal stress is 0, but I have to draw this another two more circle for this combination sigma A and sigma B and the 0 principal stress, and sigma A and 0 principal stress. Okay, so here we have three shear stress. One shear stress here, another one here, and the biggest one or maximum shear stress is this, right? Maximum shear stress is here. Okay, that means here is the center of circle, the biggest circle, right? And this radius equals to sigma A divided by 2. Correct? Okay, so let's go back to our problem. So as you saw, we have two positive principal stress. Okay, in this case, as I told you, the third stress is 0, right? The third stress is 0. And I should say that the diameter of the circle is sigma A minus the third one, which is 0, divided by 2. Okay, so that means 70 minus 0 divided by 2. The maximum shear stress is 35 kpsi. Okay, safety factor is equals to maximum shear stress at the yielding point, or we can write it in this way, SSY. Yielding point, or a strength of shear stress in yielding point, divided by maximum shear stress. and this was equal to sigma, sigma, yeah, sorry, uh, let me write again. I shouldn't delete all. N is SSY divided by tau max, maximum shear stress, and this was equal to Sy. That means the strength of the material at the yielding point divided by 2. I explained why this is equal to this, and tau max we have already found that is 35, right? So the yielding strength of the material was 100 in the problem statement. It was 100. So 100 divided by 2 and divide by maximum shear stress. So safety factor is 1.43. Okay, let's go to the second state of stress. Sigma x 60, sigma y 40, and tau xy negative 50. As you can see, in this case, the principal stresses are not given. The state of stress is in terms of x, and y components. So before, uh, it's better to find the principal stress first by using Morse circle. Okay, so I will use Morse circle equation to find the principal stress, and then we will have two principal stress equals to 68 and 32 kpsi, sigma A and sigma B. Therefore, again, sigma 3 is 0. So we can substitute to the equation that I showed you earlier to find effective stress or sigma prime, and then we will find the factor of safety, which is 1.70. Now again, here I have two positive principal stress. One of them 68. So if we draw, for example, this is 68 and this one is 32. So we have to divide the biggest one, which is 68, the greatest one, which is 68, divided by 2. 68 minus 0 divided by 2. So we are still, again, this part B, we have the first case of state of stress. The first case, which was two positive principal stress. And then we will find that by using maximum shear stress theory, we will find that safety factor is 1. Okay, in part C, again we have uh, okay, in part C we have again the stresses, the state of stress in terms of component X and Y. So in similar part B, the I can find the principal stress. Part C. Okay. As I told you, another alternative method to find the effective shear stress is using this equation. That means directly you can substitute the the stresses x and y to find effective stress. So I use directly this equation, and I will find effective stress 87.6 kpsi. And again, I can find the safety factor by using distortion energy theory. And next, we can find the the maximum shear stress. Let me write, or let me draw this state of stress here, because this is a special case. again, you can use the Morse circle theory, right, to find principal stress, but because this is a special case, maybe you can use this shortcut. As you can see, sigma x is 0. So let me draw here. Sigma x is 0 and sigma y 40. Sigma x, oh sorry, sigma x 0, sigma y 40, and tau x y equal to, let me see, equals to 45. Okay, so if I want to draw this more circle of this state of stress, sigma x is 0 and tau xy 45, maybe somewhere here 45, and the next one is sigma y 40, let's say somewhere here, and again tau xy 45. Let me draw this, right? So we have these 2 points that they have to be located on the Morse circle, at the area, at the sorry, at the circumference of the Morse circle. So let me draw this circle. Okay, after I draw this Morse circle, we can see that one of the principal stress, let's say sigma A, is positive and another one is negative, right? So I told you that the first case we had 2 positive principal stress, but here we have 1 positive and another one negative. This is the second case. So let me explain how much is the maximum shear stress at this case. When we have one negative, let's say sigma B is negative and sigma A is positive. So in this case, if I draw this Morse circle, sigma A positive, sigma B negative, I draw this circle. The third principal stress is 0, right? So I have to draw another 2 circle, sigma A and 0 and sigma B and 0. Okay, again the maximum shear stress, tau max, is equals to the maximum shear stress is the radius of this circle. Sorry, it's not, the circle is not accurate. Anyway, so because we have two we have 2 positive principal stress, we can use the equation of the Morse circuit to find maximum shear stress. Okay, and then after we find the maximum shear stress, we can find the safety factor. If you are confused about this point, you can ignore what I said here and then directly use the Morse circle equation, right? Can directly use Morse circle equation like part B. Like part B, you please use this Morse circle equation to find sigma A and sigma B. After you find sigma A and B, you will see one of them is positive, another one is negative. So when you have one positive principal stress and one negative, something like this, one positive, one negative, right? The center of circle is somewhere here. As I told you, there is another 2 circle here, and this is sigma A, this is sigma B, and the maximum shear stress is sigma A minus sigma B, right? Sigma A, the distance from here to here, minus sigma B, because sigma B is itself is negative, so negative times negative will be positive. That means A minus B is the distance from here to here. Divide by 2. This is sigma max. Okay, so you can ignore what I said earlier because it seems it's quite confusing. Again, for part B, for part C, you can find the principal stress by using Mohr-Circle equation. After you find these two principal stress, then because one is positive, another one is negative, you can find the maximum shear stress by using this equation. Okay, sigma A minus sigma B. Or directly after you find out one positive, another one negative, you can use the maximum shear stress equation again by using Mohr-Circle theory to find the maximum shear stress, and then substitute here to find the factor of safety. In case D, again I have this state of stress, right, in terms of x and y component. So don't take any risk. Use Mohr-Circle to find principal stress. Later on, substitute this principal stress here to find out effective stress, and then you will find out the safety factor by using distortion energy theory. Now, for maximum shear stress theory, as you can see, the case is different. Here, this time we have two negative principal stress. Two negative principal stress. Okay, so let me delete this. We have two, we have two sigma A and sigma B, both they are negative, right? So let me draw this more circle, maybe something like this. Sigma A and sigma B. Okay, in this case, you have to see which one of these two stresses has the, okay, before that, let me draw the third. Okay, so in this case, we have one circle here, right? And another circle like this. So the maximum shear stress, this is the maximum shear stress. So you have to see which one of these two principal stress has greatest
Both
absolute
principal
value, because
stresses are
negative, and so the greatest absolute value is important for us to find this maximum shear stress. So let's say here in this case sigma B has the maximum absolute value minus 0 to find this diameter, right, divide by 2. So this is the maximum shear stress. Let's go back to our problem. Okay, or in another way you can write this way, 0 minus negative, again here is the maximum absolute value, because this minus uh, times minus will be positive. Anyway, either you can use my method that I wrote here, maximum absolute value minus 0, or you can write in this way. It doesn't matter. So you will find the maximum shear stress. Again, this is the maximum shear stress at the yielding point divided by maximum shear stress of this state of stress, and the safety factor is 1.47. In part, I think D, the last one, 3 principal stress is given. Okay, 3 principal stress is given. Okay, when we have three principal stress, we can use this equation, right? We can use this equation to find effective stress. Part E. Okay, so we will use equation 512 to find the maximum principal stress. As you can see, what happened, the effective stress becomes zero. Right? What is the reason? Because these three principal stress are equal. Because these three principal stress are equal. In this case, when three principal stress are equal, there won't be any distortion in the final in the stress element. When three principal stress is equal, there won't be any distortion in the stress element. This is refers to the principle of this theory, distortion energy theory. You can refer to the theory and you see that this is the principle. When we have three equal principal stress, the distortion energy is zero. Okay, so the distortion energy is zero, and therefore the safety factor is infinite. That means there isn't any distortion or deformation in the stress element. And later on, we, uh, we can use as the second case to find out the shear stress, and again shear stress is zero, and because as I told you the distortion energy is zero. When distortion energy is zero, therefore there is no deformation, no shear stress, and therefore the shear stress is zero, and again safety factor is infinite. Now if we compare these five states of stress that we found safety factor by using these two theory, if we compare them, you can see that safety factor at the first example or first state of stress by using these two theory is equal. The safety factor is equal. What is the reason? If we draw the maximum shear stress theory, here shows by dashed line, okay, the line dash line is the maximum shear stress theory. Maybe I can write down this one is MSS, and this elliptic with by solid line is distortion energy theory. As you can see, these two graphs have meet each other at these 2 points, right? Here and here. That means the safety factor can be equal by using these two theory if sigma a if two positive sigma if two positive principal stress, as you can see this is two, we have two principal stress. If two principal stress either positive, two positive should be equal, or two negative should be two negative principal stress. In only in these two cases, we will get equal safety factor by using MSS and DE. Okay, so in case A, because principal stress were equal, maybe we can go back to the problem statement. Okay, two principal stress, sorry, two stress components which they were equal. So sigma, the safety factor by using this tutorial will give you same result. Okay, next. Okay, so any point, I have to mention that any point inside the region, safety factor is greater 1. Any point on the region, for example, somewhere here, safety factor is equal to 1, and any point outside the region safety factor is less than 1. Okay, any point inside the region equals to 1 equal and sorry greater than 1, any points on the region on the border of the region safety factor equals to 1, and any point outside the border of region is safety factor is less than 1. Okay, in second state of stress, the part B, if we draw the state of stress which is here, okay, as you can see, if we increase the load, right, from 0, okay, here the load is 0, if we increase up to here, right, so safety factor is greater than 1. And again, if we increase the load, as you can see, the load line, this is called load line. The load line will meet the border of MSS first, right, at this location. The load line will meet MSS borders first, and second, it will meet distortion energy theory. What does it mean? This means that MSS predicts the failure first. Predict failure. Static failure. Okay, it's difficult to write anyway. MSS will predict the static failure first at this location, and then distortion energy will predict next. That means, as I mentioned at the beginning of this problem, MSS is more conservative compared to distortion energy theory. MSS is more conservative because it predicts failure first. Let's say here the load was 0, then I increase it to 40, maybe somewhere here, then again I increase it to 50. At the 50 Newton, it predicts failure, and maybe again I increase at 60, distortion energy predicts the failure. That's why MSS is more conservative. And in part C we had one positive and one negative principal stress. Again, you can see that maximum shear stress theory will predict the failure earlier than distortion energy theory. Let me elaborate this conservativity in another way. Let's say I have a state of stress somewhere here, this point, right? If I draw a line to here, the distortion and the maximum shear stress theory is telling me that your part is failed because it's out of the border, right? So a state of stress somewhere here due to the maximum shear stress theory telling me that your part is already failed. But as you can see, this point is still inside the distortion energy border. And distortion energy border telling me that your part is safe, right? So as you can see, MSS telling me at this state of stress or predicting failure, but distortion energy is telling that in this state of stress your part is safe. That's why we are saying that MSS is conservative. So as you can see, that's why normally except this specific state of stress in which sigma A and sigma B are equal, except this, in other condition, for example, in these three state of stress, always safety factor of distortion energy theory is greater than safety factor of maximum shear stress theory. See, this is bigger than this is bigger than this, and so that's why maximum shear stress theory is more conservative. right? So as I told you, this is distortion energy theory, ms maximum stress zone, and this is load line. I think this is at the end of the problem. Yeah, here we have again that. Okay, thank you very much for your attention.